Great. Okay, thanks everyone for coming at an unconventional time. Today we're very happy to have Jim Halverson here, who's going to be telling us about neural networks and conformal field theory. So please, Jim, when you're ready, take it away.
Great. Hi, everyone. Good to see you. I am filling in for Ben today, and am happy to put something together. This is based on a talk that I gave at the IFI workshop a few weeks ago, and I have added a couple extra slides. It's worth pointing out that this is based on a paper that appeared today, right here, 2409.12222. Lots of twos in a row. So I'm excited to tell you a little bit about it. It's really about neural networks and conformal field theory, and the new emphasis relative, if you've heard some of my talks on the past, the new emphasis is the conformal part. And there's basically like one idea that you have to get. And once you get that idea, there's sort of these corollaries that come along for the ride that are interesting, but there's one central idea. So let me go to my next slide. So I am thrilled to be a part of the NSF AI Institute for Artificial Intelligence and Fundamental Interactions. If you haven't interacted with us much yet, you should. We have all sorts of virtual and in-person programming throughout the year. You can find out more information at our website here. It's an NSF-funded institute about physics for AI and AI for physics, MIT, Harvard, Northeastern, and Tufts, Boston-based, and we do a lot of fun things. So definitely come visit us. Okay, so these are the couple of extra slides that I added at the beginning, because most of what I'm going to talk about today is neural networks at a fixed time slice. But just generally speaking, there's a couple of different axes on which you might try to maximize learning. And of course, the goal is sort of given a fixed learning problem in the data, we'd like to maximize learning, generalization, et cetera. And some of the axes that we like to move along is we might consider physics-based ideas for changing our optimization algorithm, for instance. There's lots of different optimization algorithms, places you can move here. You can consider gradient descent, SGD, atom W, energy conserving descent. Many algorithms live in this space. But another axis, if you want to maximize learning, is changing architecture. And when I think about physics for machine learning, this is sort of one of the biggest open questions. I don't have a ton to say about it today, but certainly something that has changed the field a lot in the last 7 years is that in 2017, the transformer became an unexpectedly powerful architecture, and that sort of moving on the architecture axis was one of the things that really helps take ML to the next level there. So these are a couple of axes. In this talk, I'm going to imagine that I have a fixed optimization algorithm and a fixed architecture at the very least. And given a fixed architecture and a fixed optimization algorithm, I think that there's natural ways in which field theoretic thinking emerge. So in particular, first of all, we have trajectories. So associated to any fixed architecture, data, and optimization algorithm, we have trajectories in parameter space, which is characterized by some learning time-dependent path through R to the number of elements in your parameter set. You could think of that trajectory through parameter space as inducing some trajectory through prediction space or through output space, namely those parameters as they evolve are going to cause the neural network predictions to evolve. Or if you'd prefer, you can think of this as some sort of trajectory through function space itself, where the neural network is evolving through the space of maps from RD to R. Throughout, I'm just going to be taking a simple case where my input is a real number, a real vector with d dimensions, and my output is also real. That, of course, can change, but there's a tradition in high energy theory. I think it's due to Sidney Coleman, amongst other people, that sort of says, understand scalars deeply first before you try to do significantly more than that. So that's trajectories. That's about dynamics. But there's also statistics. So in particular, we have ensembles at initialization. We have thetas. We have parameters that are drawn from some distribution on parameters, and we have associated observables. So in particular, given the network phi theta of x that depends on the parameters theta, you might compute its mean prediction across all of the different random initializations. In physics, that's what we call the one-point function. And similarly, you might compute the covariance across two data points, x and y, of the network predictions this way, and that's something that we call the two-point function. So these ensembles, basically pointing out that when you start a neural network on your computer, there's nothing fundamental about it. It's really the ensemble that is the fundamental thing that's defined by this p of theta, that really we should be thinking about the statistics across the entire ensemble. And of course, putting this idea of trajectories and ensembles at initialization together, of course, what we really have is trajectories of ensembles. We have this infinite set of randomly initialized neural networks that, as you train via some algorithm, are moving along through parameter space, function space, etc. And in particular, their 1-point function and 2-point functions are changing. Their
So
average
Jim,
and their covariance. Yeah.
so Jim, thanks a lot for this already very nice and clear thing. I wanted to ask something about this. So
Sure.
here the statistics is descending from the initialization.
Mhm.
There are optimizers that are sort of intended and sometimes succeed at being kind of independent of that. Adam has some notion of that. ECD
Oh, yeah.
has measure that's based on something other than the initialization. So that's one thing, that there's a distribution there that would come more from some of the random elements in the trajectory, or in all cases the batches and so on. So I guess it's a long-winded question, but I'm wondering if there's going to be a field theory map for situations where in the end this sort of prior initial distribution is kind of screened in the screen network, but you might instead substitute some other distribution that's appropriate.
Yeah, so the way that I think about this, and I won't have a ton to say about it today, is that as the parameters update, you really have P of theta of t. So you have some time-dependent distribution of parameters. And what you're saying, like in ECD, the late time P theta of infinity, if you'd like, is some fixed thing that doesn't depend on the initial distribution. So I think of there being a time slice at every value of training time where I have some distribution. And indeed, sometimes the thing it converges to is independent of the initialization. And that's something we love. And in certain measures in cosmology, we also hope for similar sorts of behavior. So I don't have anything concrete to say there, except to say that it's interesting. But I do think it fits within this broader framework that to think from every time from initialization all the way to time goes to infinity, I can think of the associated P of theta at each time on the time slice and talk about the evolution.
Okay, perfect. So we can just say P of theta isn't necessarily just the initialization one.
That's right.
Sounds
That's
good.
right.
Okay, thanks.
So when I'm talking about the trajectory of ensembles, in some sense, the thing that defines it is the fact that P of theta itself is evolving as the parameters evolve.
Mhm.
Yeah. Good. Good. So that was I'm saying here that you could understand it with respect to the evolution of the average and the covariance of the neural network predictions, but that's determined directly by the evolution of P of theta of t itself. And then you might want to hope that in these trajectories of ensembles, you might understand how hyperparameter choices affect them and the ability to scale up. And of course, in some cases, this neural tangent kernel stuff, mu p, DMFT that Cengiz has talked about, these are some of the ideas that sort of live in this space. So NTK is famously tractable, and you can talk about the infinite time predictions and under certain assumptions and compute these things exactly. It's equivalent to kernel regression. Mu p is about scaling up, and I think all of these things admit ways of sort of thinking field theoretically. But generally, all I'm basically assuming is that some fixed architecture and optimization algorithm is determining for each neural network a trajectory theta of t through parameter space, and taken in ensemble, it's determining a flow in the distribution P of theta itself. And so I think this is a useful way of thinking. But it's the type of way of thinking that can be very hard to do numerically because it's very expensive to run large ensembles of experiments. But I do think it's fundamental. So, okay. So this sort of perspective is definitely the perspective that I brought in my TASI lectures on physics for machine learning here, which are some lectures I gave to some high energy theory PhD students in Colorado. They're brief, and I tried to keep them fun because I was having fun and the students were having fun. So it's hopefully a fun read. Some people have enjoyed them. But the rest of the talk, I'm going to be at one fixed time slice, and I'm going to be trying to understand symmetries, in particular conformal symmetry, associated to a fixed neural network ensemble at a fixed time slicing of training. And I'm imagining that could be initialization, but all I'm going to really require is that P of theta has certain nice properties. And so if at later times in training it had those nice properties, the theory would still be conformal. Okay, so these are my NNCFT collaborators. This is what we like to call this project. I've worked with a lot of other people on this sort of stuff. Mehmet and my new student Sam and Matt Schwartz and Anandita played a huge role in all of this for her PhD. But this is Joydeep, who's a student of Ning Bao, and my former student Tian, who's now a professor in Shanghai. And we put out this paper last night, and I want to tell you about it. Okay, so the outline is the following. It's a little bit more of a backdrop on neural networks and field theory. I'll repeat a couple of things. But then I'll go to what is conformal field theory and why we care. And I'll tell you something, you might know about conformal field theory, but not know about this thing called the embedding formalism. This is the thing that really shines throughout. And that's the setup. And the basic idea of this embedding formalism is an old idea of Dirac that Lorentz equals conformal. And this needs to be clarified because on the face of it, it sounds wrong, but it's not wrong. And I'll tell you what that means. So the essentials of the formalism is a new construction for conformal fields, and then we're going to use it. So there will be certain examples, free limits, deep nets, and recursion, and we'll get the free boson and we'll have some mixing. Okay. So the setup, 3 key points I want to get across. I want to recap what I just told you already about neural networks and field theory. I want to tell you about the CFT, the big picture, the what and the why. I want to tell you about Dirac's idea of the embedding formalism. And again, feel free to interrupt me at any time. So why neural networks and field theory? A network is some function living in the space of maps from RD to R. Again, I chose these dimensions for simplicity because a lot of the features are already realized. I have some parameters that are drawn from some distribution at initialization. And this distribution defines expectations, moments of that function distribution, or alternatively, the 1-point and 2-point correlation functions. And that gives us statistics and correlators. And so that's natural field theoretic language that we use in quantum field theory, albeit this is in a different description. And then we add dynamics for learning. Okay. What we like to call the neural network field theory correspondence is that the essential neural network information is the choice of architecture together with the choice of some parameter distribution at some time slice, maybe initialization. Zimming, could you mute? Thanks. And this defines a field theory with a partition function of this form, where this way of computing goes back to works by Neal and Williams in the 90s, where you compute correlators of correlation functions or average predictions or average covariances, if you'd like to think that way, covariances of neural network predictions rather. You compute them in parameter space. And it can be related in certain cases to the version we learn in field theory, which is this form, the Feynman path integral. But basically, this information is already enough to define this partition function, and therefore this is enough to define a field theory. And sometimes, if we're lucky, when we write correlation functions this way in this parameter space description, we can compute some things non-perturbatively exactly, and that's what I'm going to tell you about. So in this setup of neural network field theory, you might ask a question: can I engineer my defining data to get field theory plus X? I'll say in the context of when I think about this line of research that I do, I give a very broad definition to field theory. For me, a minimal necessary condition to call something a field theory is it has to have fields, and it has to have notions of correlations. There's the correlation functions. There's many fields, and so we have some ensemble of them, and we can compute correlators. People sometimes want to demand that field theories satisfy extra things. Maybe you demand that they be quantum or Lagrangian or symmetries, etc. The problem that I sort of find with demanding any of these as a necessary definition of a field theory is that you find some other community of physicists that is willing to abandon them. I like to view it as these correlators are the central thing. And then it's a question of engineering to ask, can you add some extra property X? And today, X is equal to conformal. So this is this thing that we've been working on for a little while. Okay, so hopefully that's clear enough. Maybe it's worth saying, we understand quite a bit about symmetries. In certain limits, we know how to get local theories. In certain cases, we know how to compute Lagrangians. Quantum is harder. We don't really have many interacting quantum theories in this context yet, unless they're secretly local Lagrangians. But this is hard for reasons I can get into if people are interested. Okay, so what is conformal field theory? So a field theory with a conformal field theory is a field theory with a conformal group as a symmetry. That is coordinate transformations that leave the metric invariant up to an overall position-dependent scale factor. The group of a Euclidean conformal field theory in d dimensions, the symmetry group, is SOD plus 1, 1, and it's made up of rotations, translations, scaling, and something that I don't really need to get into too much called special conformal transformations. These are important because conformal field theories describe phase transitions in physics. And in particular, I have this phase transition here where I asked GPT to show me the Charles River boiling. And interestingly, it's in winter. So the Charles River is boiling, but you see snow on the ground over here. So somehow we're close to the triple points of this system where everything's coexisting. Secondly, from a renormalization group perspective, something that sometimes people like to think of is CFTs are the bookends of QFTs. Namely, they like to think of the space of QFTs as having a CFT in the UV that you then perturb. And CFTs are fixed points of renormalization group flows. So when you deform by a relevant operator, you follow some flow down to some IR CFT. And so it's not just relevant for describing phase transitions, but it's also relevant for thinking about formal field theory and thinking of this as bookends of QFTs. Okay. So what Dirac pointed out and thought about is that the conformal group the Euclidean conformal group in d dimensions is SOD plus 1, comma 1, and that's also the Lorentz group in 2 dimensions higher. So that was his insight, which just looking at the group SOD plus 1, comma 1 is kind of obvious. And so he suggests that Lorentz equals conformal. And what that means is a Lorentzian, in some sense, the Lorentz group 2 dimensions higher is equivalent to conformal group 2 dimensions lower. And so this is his embedding formalism. This is something that's all over the CFT literature, but we're going to use it in a new way today. So what he points out in the technical lingo is that the Lorentz transformations in d plus 2 dimensions induce nonlinearly realized conformal transformations on the d-dimensional projective null cone. The way that this works is that I'm going to take my d plus 2 dimensional Minkowski coordinates and split them into I and j that run from 1 to d, and then I have some light cone coordinates plus and minus in the usual way in physics. So from a Lorentz group perspective, these Lij's become rotations in d dimensions. The L plus minus become scale transformations. The Li plus become translations, and the Li minus become special conformal transformations. So this is how the story goes. It's worth saying that 2 of these types of transformations, when you act with them on a point on this projective null cone, it actually sort of takes you off the section and you have to rescale back, which is why it's nonlinearly realized. But this map has been worked out in glorious detail in the CFT literature, and you can even find it in classic modern lecture series like Rickoff's EPFL lectures or Simmons stuff and Stasi lectures. This is just there. Okay, so the way that it works is the following. This is the way that the transformations map to each other. The way that it works at the level of geometry is that I have d plus 2 dimensional Minkowski space. And I'm going to write my x0 coordinate here and my d plus 1 coordinate here. And I'm going to have a copy of RD in this x coordinate. So you go to the null cone and you go to light cone coordinates, and then you projectivize. And in these light cone coordinates, you choose x plus equals 1. And this is called the Poincare section. Just looking at this, it's on the null cone in the higher dimensional space under this metric. But there's this x here that's left over free. So it's a copy of RT. Okay. So that's the basic idea is, I'm trying to remember what slide comes next. Good. That's the basic idea, is to relate Lorentz invariant quantities on this space to conformally invariant quantities on the Poincare section of the projective null cone, which is this set of coordinates, by restriction. So in using this in modern CFT, this, as I mentioned, is textbook in modern CFT. So what happens is that a conformal field gets lifted on to d plus 2 Minkowski, and it's homogeneous. So I have this d plus 2 Minkowski coordinate here, and I have a field that is homogeneous on that space. And it restricts back to the conformal field by taking the field on the higher dimensional space and restricting to the Poincare section. And one more time, the Poincare section is this coordinate here, and it's a copy of RD. Okay. So the primary focus on the literature is the way that Lorentz symmetry sheds light on conformal objects, such as correlation functions. It's really sort of about conformal kinematics. And when you cast it in that language, in the embedding space, in the d plus 2 dimensional space, you have a correlator that looks like this. This is a dot product means Minkowski dot product here. So this is a Lorentz invariant quantity. But when you restrict to the Poincare section and do a little bit of algebra, what you find is that this x1 dot x2 becomes x1 minus x2 squared. And you have something that's Lorentz invariant becomes something that's translationally invariant. And in particular, this 2-point function is fully conformally invariant. It's worth pointing out that normally in field theory, the second we say Lorentz invariant, we're really thinking full Poincare invariant. So it's invariant under translations as well. This theory, a priori, is not necessarily invariant under, and as written, it's not invariant under translations. So this can be a non-Lorentz invariant, sorry, a Lorentz invariant, non-translationally invariant theory where the translation invariance in the CFT is descending from the Lorentz group. Similarly, the 4-point function can be written in this form. This is where the interactions in the theory live. And there's something called crossing symmetry that imposes a particular identity that has to be satisfied by this GUV that determines the 4-point function. This GUV is a canonical way of writing the 4-point function, and these U and V are something called conformally invariant cross ratios. Okay. Good. Trying to remember what's next. I think I'll be at a pause point in a second. So the embedding formalism is a powerful tool for understanding how conformal invariance constrains the correlators of known CFTs, or CFTs we're searching for with constrained optimization. Physicists call that search for CFTs with constrained optimization the bootstrap. But the question that we want to ask in this talk is, can we use the embedding formalism to actually construct conformal fields in a new way? And that's something that, to my knowledge, has not been done in literature. And this work that came out today with NASCAR and Tian. Are there any, it's a small intimate group, are there any sort of questions on the basics of the embedding formalism, or is it good? Okay. Well, I encourage you to interrupt if not.
It's good. The open question is how useful it's going to be, and that's what you said you're going to start talking about.
Okay, good. Yes, utility is something. I will have examples. How useful they will be is another question, but we can talk about that. But the claim is that this version of the construction is new. Great. So the question we're asking, can we use the embedding formalism to construct CFTs? So what we have is a construction of this form. So to define an SOD plus 1, 1 symmetric homogeneous theory on D plus 2-dimensional Minkowski space and restrict it to the Poincare section of the projective null cone, which is this copy of RD, and have this Lorentz symmetry in this higher dimensional theory descend to conformal symmetry on RD. So the constraints on the D plus 2-dimensional theory are the following: homogeneity, Lorentz invariance, that's the crucial symmetry in the higher dimensional theory that gets you the conformal invariance. And finally, correlators. There are places where, if you're not careful, you can end up having your correlators diverge everywhere and sort of the theory doesn't exist. So you have to make sure that your correlators are finite in the sense that they don't diverge everywhere. So those are the 3 principles, and we'll go through them one by one. So principle 1 is homogeneity. This is the thing that the neural network construction sort of really just allows from the get-go. So just to get homogeneity, you just let phi be a neural network with a homogeneous architecture. And there's a technical point that this is important for the well-definedness of the partition function after the projectivization. But you sort of get it for free. And so as a simple example, an MLP with a homogeneous activation is something that is a homogeneous function and could serve this purpose of providing a homogeneous neural network for the construction. Alternatively, just making something up, you could use compositions of homogeneous polynomials. That hurts expressivity, but potentially, might increase the control due to connections to other fields. Maybe stating some hopes that I have for the future. But homogeneity is easy. You just need a homogeneous neural network. Principle 2 is Lorentz invariance. So this can be shown at the level of partition function, but I'm showing it here in terms of correlators. So these are the correlation functions of the neural network field theory. Remember that this is this phi of x is an architecture that's been inserted here. P of theta is some function, or in some cases probability density function that's associated with the neural network parameters. And the correlators are defined this way. This is the usual way that they're defined in, for instance, the neural network Gaussian process literature. So we need these to be Lorentz invariant. And an upside is that the measured d theta here is an ordinary integral. So as long as things don't diverge nastily, no question about well-definedness here. Good. So the symmetry mechanism from a paper a few years ago is to choose an invariant P, transform the fields under the symmetry, absorb that transformation into a redefinition of the parameters, and then you get invariant correlators from the invariance of P. So in our case, we just need to choose P to be Lorentz invariant. But it's pretty easy to write down Lorentz invariant functions P of theta. So that's not that hard either. Yeah, so this is our symmetry mechanism, maybe in case some of our original work involved rotation symmetry, some follow-ups involved translation symmetry. And then, for a while, we thought about conformal symmetry, and it's harder. And this Lorentz trick is the way that we're approaching it now. Finally, finite correlators. Good. So a natural idea would be, to get a Lorentz invariant P by Wick rotation from a famous rotationally invariant P. And so I'll show you by example why you have to be careful. So if you just take P of theta to be a standard Gaussian, and you Wick rotate by sending theta 0 to I theta 0, you get the wrong sign on this Gaussian, and this is not normalizable anymore. And this is the sort of problem that you can run into if you're not careful. So, the correlators are associated with this essential singularity. And this is really the main technical difficulty in the construction. The two of the three principles, homogeneity and Lorentz invariance of P of theta, easy. Making sure that you can write down these correlators and that they don't sort of diverge everywhere is the main technical difficulty. And, that's where you have to put in the work. So just recapping the formalism, we start with a Lorentz invariant theory, a Lorentz invariant homogeneous theory of neural networks in D+2 dimensions, and we restrict and we get a CFT. Or I should say a conformal field a little more conservatively. And we have these three constraints: homogeneity, Lorentz invariance, and correlators being well behaved. So, that's it. Here's a cake and here's a decorated cake. Those three principles are the bulk of the cake in the story. It's based on this crucial idea of Dirac. And, the key thing that wasn't sort of possible in the previous literature when people study kinematics with the embedding formalism is that to define that theory in higher dimensions in terms of fields, you need homogeneous fields. And we don't normally define field theories in terms of some functional form of the fields, which is sort of exactly what we do in this neural network description. So that's sort of the thing that the neural network is buying us, is a description where we get to specify the form of these fields and we get homogeneity. So the rest of the talk is sort of just decorating the cake. The cake is already there. I'll give you a simple pedagogical example just to show you that it works. The emphasis is on pedagogy. I'm not trying to convince you that's a super interesting example. I'm trying to convince you that the formalism works. I'll give you a more clever example. There's probably lots more clever examples. There's a generalized free theory limit that you can take in this setup. That's like the neural network Gaussian process. You can talk about deep nets and recursive CFTs in a way that was interesting to me, and we'll talk a little bit about the free boson and mixing. So that's it. That's the essentials of the formalism, and the rest of the talk is decorating this cake. So let's use the construction. Christian, can you remind me, am I supposed to aim for like 45 plus 15? Is that the...
Yeah, I think nominally, 45 plus 15 was the target, but we can be a little flexible.
Yeah. No, I think I'll be about 45 plus 15.
Thanks.
Okay, so let me use the construction. So here's a solvable non-unitary example. So one approach is just to start with a rotationally invariant theory in D+2 dimensions, Wick rotate to get a Lorentz invariant theory in D+2 dimensions, and then restrict. So we'll solve a Euclidean D+2 theory, Wick rotate the correlators, and push down to get the CFT. This is just like a totally trivial architecture just to make the point. The Euclidean field is theta.x, where here this is the Kronecker, Euclidean dot product, and P of theta is rotationally invariant. When you take this structure and you compute the expectation in parameter space, you can factor this x out of the expectation for the 2-point function, and then rotational invariance makes it proportional to delta ij and contracts. And so the 2-point function in particular is x1 dot x2. And you can also compute the 4-point function. It's x1 dot x2, x3 dot x4 plus permutations. And this mu4 is the fourth moment of the theta distribution.
Jim, sorry to interrupt. There's one question in the chat. It looks like
Oh,
Mike
yeah,
is
I'm sorry.
asking, do standard constraints on CFTs like associativity or reflection positivity turn into simple constraints on the kernel P of theta was the question. I think the answer is no, but you can give a better answer.
No, yeah. Mike, I think one of the big open questions in this whole setup is reflection positivity. So from my understanding of the bootstrap literature, admittedly as an outsider, I'm someone who normally lives more in SUSY world than conformal world, but reflection positivity in that context is often thought of as constraints on OPE coefficients via the relationship between the OPE coefficients and the correlators. For those of you that don't know, reflection positivity is a very famous constraint that's relevant for unitarity of it's related to unitarity of Euclidean field theories when you rotate them back to Lorentzian. So that's a very important constraint, and I think that that's something that's like perhaps the major open question for this direction, because that's really about turning statistical field theories into quantum field theories. Associativity, maybe you're thinking about things like crossing, and I'll have something to say about crossing in these examples. Yeah, thanks, Mike, for the question. Good. So I have this G4 here. This is just computed exactly. Yes, it's a simple example, but this is an exact computation. And so this pushes down to an interacting CFT, where you do the standard thing where you pull out these particular x1 2 squared is x1 minus x2 squared, x3 4 squared is x3 minus x4 squared. So you pull out these canonical combinations, and you can write this in this GUV. You can write the 4-point function in terms of this GUV, where U and V are these conformally invariant cross ratios. In this case, it's exactly this form. We have it exact bang on. And this is one thing that's true. So given an exact 4-point function in a CFT like this, you can express crossing just as a simple constraint on GUV that this happens to satisfy. And it's basically required by conformal invariance. This is to be contrasted with the bootstrap, where in the bootstrap, what we do, what people do is that they're trying to satisfy certain constraints that are necessary for conformal invariance via the crossing equations and so forth. But they're sort of searching for CFTs. This is conformal by construction, and so this has to satisfy crossing, and it does.
So are you saying this is this could be in any dimension, any dimensionality?
Yeah, it seems like it. One, of course, obvious subtlety is that in 2 dimensions, the global conformal group gets enhanced to a bigger Virasoro and so forth. We didn't look into that much, but I think it's something that in principle is doable.
And the central charge of this, the central charge.
Yeah, these theories don't necessarily have to have stress tensors. So we will construct the free boson, in which case you get the normal central charge. This was something that you and I talked about when I was visiting Stanford in May. And one of the developments since then is that some of my friends who are bootstrap experts that I relied on heavily sort of said, stop asking the question, what is the stress tensor, which is a very Lagrangian way to think about things, where you write down the Lagrangian and the action, and then you take appropriate derivatives and you say, here is the stress tensor. What they were saying is that you should assume an OPE, and you should do a conformal block decomposition and ask whether there is a stress tensor actually contributing to the 4-point function. And in some of our cases, it looks like there's not a local stress tensor. So in such a case, I don't know what to say about central charge. But in principle, Eva, if you were able to identify the stress tensor in these setups, you would just compute it in the normal way. So.
Okay, thanks.
Yeah. Okay. So this is an exact conformal 4-point function of this, simple theory, and it uses the embedding formalism crucially. And this 2-point function is the Lorentz invariant thing that pushes down to the standard conformally invariant thing, 2 dimensions lower. Okay, so there's this other example that we have. So remember that our constraints are more important than the details of the example is sort of the philosophy. Our constraints are homogeneity, Lorentz invariance, and making sure our correlators don't blow up everywhere. And then you sort of realize that the correlators are integrals, and you sort of start asking what communities in physics are concerned with making sure that Lorentz invariant integrals don't blow up everywhere. And that's basically what the amplitudes community is doing. So there's this really, I was unaware of it. I knew that there was a growing literature, but it's a pretty beautiful, increasingly mathematical literature about deep ways to try to understand finite integrals. And so if you make appropriate choices, here, so if you take the architecture to be theta.x inverse, and I choose this one because this guy satisfies the unitarity bound. So it satisfies a necessary condition for unitarity, and it potentially is unitary, and we can talk about that. And then if I take p of theta to be 1 over theta squared plus 1, indeed, one shouldn't really call this a probability distribution anymore, because it can be negative, because this is a Lorentzian contraction. But then when you write down correlators of this type, the correlators of this construction actually look kind of like Feynman integrals, and you can use both the techniques and the packages in Mathematica written by the amplitudes community. So that's what we did. So the package gave us this answer very quickly, but we're outsiders, so we had to do it all by hand to make sure that we understood what we were doing. But the amplitudes community is developing many techniques for evaluating Lorentz invariant integrals. That's what loops are. And there's something called integration by parts identities. And what the integration by parts identities do is that they give you relationships between different Feynman integrals that can be turned into differential equations for the Feynman integrals that you can then solve. And so when we use this, rather than trying to compute this integral, we solve the diffie-q for the Feynman integral such that up to an overall constant, this constant c here, the 4-point function is of this form. It's kind of an unusual 4-point function, but is still a conformally invariant 4-point function, exact in this setup up to this constant c that we didn't determine. And what was the other thing I was going to say about it? And it satisfies crossing. So you can do a conformal block decomposition, study the spectrum for OPP properties, etc. So this is just one example. I just highlighted an example on the last page 1 here. But basically, at the end of the day, what this construction is telling you is that we're going to get conformal correlators by Lorentz invariant correlators 2 dimensions higher. So we really should be paying attention to what amplitudes people are doing with respect to Lorentz invariant integrals. And this was useful in this case. I don't know how far it goes, but it gave us another example. Okay, let me start getting more corollaries for you, because you might look at this and be like, that's a really stupid neural network, and so is this one. Of course, we know that it's really deep networks that are giving us strength in machine learning. So if you have, there's something that we call a CFT layer. So if you have any conformally invariant input layer, for example, something like this is conformally invariant once you have P Lorentz invariant and finite correlators. What you can do is you can take that CFT layer at input and act with any homogeneous layers after it. And as long as the correlators remain finite, what you have is a conformal field inherited from the CFT input layer. You have a conformal field at each layer. So the conformality is sort of established at input. And then as long as you maintain homogeneous subsequent layers together with finite correlators, you pick up the formalism for free. So in particular, if you have a conformal field at each layer, there's some sort of recursion relation amongst the CFT data. In general, this is the CFT at the jth layer, and the conformal dimension of it is the CFT dimension at the j-1th layer times whatever the degree of homogeneity of the layer in between is. And you can do this for deep linear networks, and you can find that the conformal 4-point functions at layer L depend on the conformal 4-point functions at layer L-1 according to some appropriate moment tensor of the weight distribution in between. So you can sort of stack these things and make them deeper. It's not just like this totally trivial stuff at input like I was showing you initially for pedagogical reasons. You can also take a free theory limit. So what I can do is take one of these conformal fields and take n independent copies with some weights wi multiplying them and sum them up. And the weights, for simplicity, I take IID satisfying certain properties. And the CFT data that you get for this phi here, these are conformal, but I'm forming another conformal field out of them. The 2-point function is preserved for all n. But as n goes to infinity, you get this exact 4-point function here, where this is the GUV that determines the 4-point function of an individual phi theory. This is a free theory that it's asymptoting to, and as n goes to infinity, you get less of this and more of this. So it's interpolating between an interacting and a free theory. Good.
Sorry, I'm so sorry, Jim, but I always have the same question at this point, and I'm just kind of slow on the uptake. A full field theory is like a functional integral over the,
Yes.
the field is infinite dimensional, whether interacting or not. And
I would say good. In normal descriptions, yes, it is infinite dimensional. And this is this finite dimensional thing you and I always talk about. But I can take it. Anyways, yes, I know what you mean. What's your question? I think I missed it.
Well, so that's why I'm confused. I always get confused about the tying together the finiteness of n here and interactions, because those two notions of being interacting or being regulated and made finite are different notions. That's in general.
Are you asking what I mean by interactions in finite n?
Well, you're just tying the two together, and I'm asking whether they should go together or not. In other words, there should be a way to go to. One way to say it is, you should be able to retain interactions while going back to the full field theory. So removing the regulator, in other words. Which
Yeah,
maybe somehow that's related to the mu parameterization in this world of neural network.
Sorry, I can answer your question, I think, very clearly. This is something we worked at pretty in glorious detail in the paper with Matt. You're asking, can't I get interactions at infinite n? Because I can in normal field theory as well, right? So the Gaussianity, Eva, in this case here, under these assumptions, the Gaussianity at infinite n, which Gaussian for me definitely means not interacting. There's no connected correlators. The Gaussianity comes from the central limit theorem. And so then the way that you get interactions is by parametrically violating one of the assumptions of the central limit theorem. One way to do that is in 1 over n, and you can compute the connected correlators and see that they're 1 over n suppressed. So as you make n finite, you're getting some interactions in the connected correlators. But as n goes to infinity, another thing that you can do is you can break the independence of the things in here. And that independence breaking is breaking one of the assumptions of the central limit theorem that can also induce interactions at infinite n. You can definitely get interactions at infinite n also. It's just a different mechanism. You're violating a different assumption of the central limit theorem. Does that make sense?
Yeah, it does. So here we're putting here we're just tying them together, but we wouldn't have to.
That's right. This is under the assumption of IID, and under the assumption of IID, I move the 4-point function changes in this way. This 4-point function here is the 4-point function you would get in a free theory. This is a interacting theory 4-point function, by which I mean that the associated connected correlator is non-zero. And it interpolates, but there's an extra effect that I'm not including, which is basically coming by making this IID assumption. That effect is thrown away, and that's from independence breaking. So there's definitely another potential effect that you can mix in.
Okay, thanks.
Okay, cool. Yeah, great question. Sorry that wasn't clear before. Okay.
And there's one other question in the chat, if you have time. What does the neural tangent kernel limit map to on the CFT side? That's the question.
I mean, the NTK limit is kind of related to these Gaussian process limits. In fact, if you look here, the normalization that I used here is actually the NTK normalization. This is not a neural network Gaussian process normalization. So indeed, if you'd like, in that language, this 2-point function is written. This 2-point function that I'm getting is written with this field in the NTK parameterization. But there's a key difference between the 2-point function and the NTK. So that the NTK is an appropriate number times the 2-point function plus some extra stuff that comes from derivatives further down the network. So you could compute that here, but because I'm not training, I'm not computing the NTK. I'm just computing the 2-point function. If you're familiar with it, the statement is that if you take the 2-point function of this theory and you take the NTK under the assumption that you only update the last layer weights, they become equivalent up to a constant. So they're deeply related, but I'm not talking about NTK here.
Also, in mu-p type of parameterizations, people learn this important feature. So maybe they are more interesting in CFTs or something. Do you have any comments on that for mu-p type of parameterization?
Good. Let me think. Yeah, I mean, you can ask what happens to the field theory description in the mu-p scaling, and the answer is the 2-point function gets beat down to 0, and you just have a 1-point function. So it's kind of an unusual thing. CFTs have 2-point functions, so I would say that I wouldn't, that's some sort of mean field theory, which is the language Cengiz would use. But CFTs, sort of by definition, have 2-point functions, and in that limit, those get beat down in mu-p, as far as I recall.
Okay.
So that's interesting, because in mu-p, right, the whole point is you preserve representation learning in that limit, and it's thereby it's much more strongly interacting, much more complicated. But
That's what
Yeah, I guess I haven't thought enough about the connections of this to mu-p. It's a good question. But NTK and NNGP, which is what I'm sort of related doing here, they're deeply related. The NNGP kernel appears in the NTK, and they're equivalent up to a constant if you shut off learning and everything but the last layer. Yeah, I should really understand how mu-p connects to this. This is a good point. Yeah. I think I'm almost done. I can finish up and then I'll take more questions. So we can get the free boson. That's good. And just sort of in conclusion, the one thing that you were supposed to get out of this is that the embedding formalism relates Lorentz invariance 2 dimensions higher and CFT 2 dimensions lower. The Bootstrap community and the CFT community uses that for kinematics. But because the neural network lets you define a homogeneous function here, you can use it to construct Lorentz invariant theories here and restruct it to new CFTs. Maybe not new CFTs, but a new construction of CFTs. This is not normally how people do it. So there are constraints, homogeneity, Lorentz invariance, and making sure the correlators don't blow up. And then we decorated the cake. There's a simple pedagogical example, a more clever example, generalized free theory limits, deep networks, recursive CSTs, and the free boson and mixing. So, you know, Lorentz invariance equals conformal invariance is this paper from 1935. And yeah, anyways, this was something new to me and I had a lot of fun. So thanks a lot. I'll take questions.
Okay, great. Thanks, Jim, for the very nice talk. Let's open the floor if anyone has questions. I don't know if we need to raise hands or people can just jump in because it's a small group.
Sorry if that was too physicsy for people that are from computer science backgrounds.
I guess I have one naive question that might be more about embedding space than about the neural net's realization specifically. But is there a systematic way, once you have a CFT constructed in this way, to do conformal perturbation theory around it, like add a little bit of a relevant operator, which I guess would, I mean, maybe there's a geometric way of doing it by deforming your embedding space or something?
Yeah, I haven't thought about that super systematically, but definitely because the defining data is the architecture together with P of theta, deformations in that language are necessarily corresponding to either an architecture deformation or a deformation of P of theta. So if you add a small Lorentz breaking deformation to P of theta, that would sort of be the equivalent of turning on a conformal breaking operator, like a relevant operator in the CFT. So I haven't studied that in detail, but that, you know, that's the starting spot, I think.
Mm-hmm.
Yeah.
Good. Other questions?
Since there's quiet, let me just ask
Sure.
what may be just a very silly question, but you know, in your neural networks, you're always in some limit, and maybe this is just some confusion, but outside of that limit, is there anywhere you can imagine, you know, an ordinary neural network that one implements having something to do with a conformal field theory in the same way?
Yeah, no, that's a great question. So I think the limit that you're talking about, Paul, is this n goes to infinity limit I'm taking here. Is that right?
Yeah.
Right. Yeah. So all of the things I'm saying can happen at finite n as well. Maybe I should a little bit of the history of this large n limit in the neural network world is that in the 90s, Neil showed, and Williams did some computations following up Neil, that these neural networks are drawn from Gaussian processes on functions in the n goes to infinity limit, where n is the width. And in our language, that's just the generalized free field theory. And so in some sense, field theories were already related to neural networks then. Some of the interest since 2019, I think Sho Yaida wrote the first paper on this, and then I wrote one, and then Dan and Sho's book came out, and there's been a sort of a flurry of activity, and certainly in the CS community too, where I'm not as familiar. But people got interested in 1/n corrections. And the way that the story goes is that as you take the large n limit, and n being more general to real world neural networks, since you asked about it, n could be the width of an MLP, n could be the number of channels in a CNN, n could be the number of heads in a transformer for multi-head attention. So there's many n's that appear, but when you get this free theory limit at large n, it's always happening because of a central limit theorem under the hood somewhere. And so what people got interested in is they got interested in characterizing 1/n corrections so that they could understand the theory of finite neural networks. And in particular, those 1/n corrections, because you're not in this, you know, you've backed off the central limit theorem a little bit, they're necessarily going to correspond to some sort of interactions. And the way that you can show that is if instead of computing G4, you compute G4 connected, you can show under relatively mild assumptions that it scales as 1/n. And so this is sort of measuring the non-Gaussianity via the connected correlator. So there's a pretty extensive literature on that. And sort of everything I said today, like, for example, this silly little example that I did earlier, I don't have n anywhere here. All I'm sort of doing here is taking the things that I did previously and sort of stacking them and summing them up. And I'm taking a central limit theorem limit where they're becoming free. So you can do this stuff at finite n as well. But definitely but both out of interest for physics reasons and also to touch on to what the neural network community is sometimes doing, this large n limit becomes free. So you can do both. It's finite and it's infinite.
Excellent.
Yeah. And I actually learned conformal field theory from your notes when I was a PhD student. So
And you got to teach it back to me.
no. So, but yeah.
Good. Other questions?
I have one kind of exploratory question. So large and conformal field theories have implications in holography. Would it be a stretch to say that now this neural network representation in such a limit would have a connection there?
Yeah, I mean, to me that this this large n limit is a free theory. This CFT is a free theory. It's not some strongly interacting CFT like we would normally look at in holography. I don't see how to make the connection directly. If there is, certainly it's something I would be interested in. But the large n here is really for Gaussianity, is for the central limit theorem.
I think that question also relates to the discussion about the stress tensor, which you
Yeah.
could try to build in, but didn't
Yeah.
do as you explained, right?
Oh, one thing I meant to say is that part of the reason about talking about the free boson is that the free boson does have a stress tensor in D equals 4. So, that's one case where we do get a stress tensor, but sort of how to systematically build it in, I think we don't fully understand yet. I'm sorry I don't have a better comment on holography. Maybe it's worth saying one thing that we were, maybe people here know the answer. In various places, I didn't talk about it, but we did a conformal block decomposition, which assumes OPE and so forth, standard stuff. And normal, like for example, when mathematicians define CFTs, they love talking about operator algebras and really starting with OPE as central. And if you have unitarity and state operator correspondence, OPE is like a corollary and it comes along for the ride. But like in complete generality, if I don't assume anything else, is there a guarantee that I get an OPE in a CFT? So in particular, what the question I'm asking is, if I have conformally invariant correlators and I don't assume unitarity or anything else, it's not entirely obvious to me that the standard proofs I know of the existence of an OPE assume extra assumptions. I don't know if anyone has a comment. Do all CFTs have OPEs, or are there CFTs that have conformally invariant correlators, but it doesn't make sense to talk about an OPE? Kind of a weird question because we're normally unitary, but.
Yeah, I don't know the answer to this, but I mean, maybe an interesting example to think about is the celestial CFT, if it exists, I think is believed not to be unitary, and it also has strange singularity structures. Like if I remember correctly, you can get divergences both when operator insertions become coincident in this putative celestial CFT, but also when they're antipodal. So, I mean, it's not quite what you're asking, I guess, about whether there's an OPE, but the structure of such an OPE would be different because you can also get divergences at separated points. So I mean,
yeah.
Maybe that's a non-unitary example that helps, but I don't know enough about it.
No, that's an interesting, yeah. I'm not familiar with that fact, but that is a pretty significant deviation from the norm. I agree.
So you have thought about symmetries of the network and changing the input. You could also potentially think about symmetries of the network in terms of reparameterizing the network. So for instance, if you think about a multi-layer linear network,
Yes.
then there is a very large symmetry group under reparameterization. So is there a possibility of using any of your results thinking about reparameterization of the input to
Yeah,
information about reparameterization symmetries of the network.
I think you mean reparameterization symmetries. That's a non-trivial map on the parameters that leave the function invariant. Is that right?
Yeah. Mm-hmm.
Yeah. So that is definitely a type of symmetry that arises in actual networks. And I imagine you have things like permutation invariance and MLPs in mind or something like that. That can happen. One of the things that's sort of distinct from normal symmetry stories in ML here, it still should be a symmetry story in ML, don't get me wrong, but people often talk about invariant or equivariant functions. In physics, and what you're talking about is symmetries of the parameters that leave the function invariant, that just transform the symmetries. That's about invariance under some transformation. In these setups in physics, the fields generally transform non-trivially. They take you to other functions. But the thing that's true is that there's symmetry in the whole ensemble. So for example, if I have a neural network phi and I have phi of x, phi of y, and imagine that I rotate them. So I have phi of rx and phi of ry multiplied. If that function, if that neural network is invariant as a function, then it's equal to phi of x, phi of y. But what physicists are normally interested in is invariance under the expectation. So you have to surround it by boldface E. So it's cases where the networks aren't necessarily invariant, but the ensemble is. So in a setup like this is a case where some neural network would have an associated Gaussian process kernel that has a symmetry, but the actual neural network itself doesn't. It transforms non-trivially. So it's related. I mean, I think it's definitely, these concepts are all related, but the one you asked about, as I understand it, was about invariance of the function as opposed to invariance of the ensemble of functions. And I think these are a little different. One's a weaker notion.
Great. Any further questions for Jim?
Hi, Jim. Thanks for the talk. Just a quick question. So you mentioned that by using this embedding formalism, you can get Lorentz invariance, but not translation invariance in like the full Poincare group.
I didn't say you can't get translation invariance.
Okay.
I said you don't need it.
Okay. Okay.
So let me go back to that. Sorry, where were we? Here, yes. Yes.
So okay,
maybe I answered your question.
probably I misunderstood. So I thought that in the theory, like in the Lorentzian theory, you don't have translation invariance once you describe it starting from the CFT in 2 dimensions more. But probably misunderstood.
I didn't. Good. I don't think we're saying anything that's contradictory. I am not saying. I'm not saying that you never have it. I am saying that you don't have to have it, because the point is that the translations that you need are the translations in the CFT, and the translations in the CFT are coming from the higher dimensional Lorentz group according to this map. So the translations are coming from these type of Lorentz transformations, and so in particular, a correlator that is of this form is Lorentz invariant but not translationally invariant, and it's sufficient. It's sufficient to push down to something that that is fully translationally invariant. So I'm not claiming that you never have it. You could do extra engineering to get full translation invariance higher up, in which case, let me just think of it in this form. If instead of writing this, I write x1 minus x2 quantity squared, that's translation invariant. And then I expand it out. And then when I restrict to the Poincare section, the x1 squared, because I'm on the null cone, and the x2 squared are both 0, and you restrict to something of this form. So you can have more symmetry, but for our purposes, if what you care about is Euclidean CFT, you don't need it. So it's a little unusual. So I'm just pointing out that this is a Lorentz invariant theory that doesn't have to be translation invariant if all you want is CFT, and it also need not be unitary.
Okay, thanks.
Yeah, it's unusual. That's why I emphasize the point.
Yeah, thanks.
Great. Any more questions for Jim? Okay, well, maybe we should thank Jim again.
Thank you, everyone. That was very fun.
Thanks.
Thanks for letting me pinch hit last minute. So.